what I want to do at this stage is spend a couple of minutes going through some notation, and it's just notation. It's all my goal for today is to talk about notation. And the reason I want to talk about notation is because this notation is universal throughout the quantum community. There is mathematically or almost mathematically no content to this notation, but every time you change notation, you create this extra friction for the reader and for the other person that you're talking to. And so it's really important that we acknowledge that this notation is out there, that you are comfortable with the notation, and that you don't see it as an extra level of encoding obfuscation to getting to doing computations with quantum mechanics. To be completely clear, the quantum mechanics that we do when we're doing quantum information theory, when we're doing modeling quantum computations, is the multiplication of finite dimensional matrices by vectors. And it's not any more complicated than that. But this notation that's been invented, the so-called ket notation, is it's in some sense doesn't add anything, but in another sense it does. So there's one particular computational way in which the ket notation is very helpful, and that is when you transition to large dimensional vector spaces. So yes, you can work with ordinary vectors and matrices when you're talking about quantum mechanics all the way through. But when you start wanting to talk about vectors in high dimensional vector spaces, this ket notation, which I'm about to introduce, turns out to be a little bit more efficient to do that. And if you don't introduce this notation, then you'll end up trying to invent some proxy for this notation. So let's get straight to it by reminding you of the postulates of simplified quantum mechanics. So if you remember quantum mechanics, simplified quantum mechanics as I presented it last time, there were 6 postulates. I'm really going to focus on the first of those postulates, namely that to every physical system, there is assigned a Hilbert space, and the Hilbert space H is, for us, in simplified quantum mechanics, a finite dimensional complex vector space with an inner product, angle bracket, comma, angle bracket. And just to remind you, the elements of our Hilbert space are vectors, which are column vectors of complex numbers Vj, where Vj are complex numbers, right? And this inner product, angle bracket, comma, angle bracket, well, what does it do? It takes 2 vectors, a vector V, a vector W, and it produces a complex number, not always a real number, but sometimes a complex number from these 2 vectors. And it kind of measures the, if you like, the overlap of one vector on the other. We think of it in quantum mechanics as more measuring probably, or being a precursor to the result probabilities of, and the outcomes of measurements. So let's now talk about kets. Now, before I do that, I'll just focus on this inner product here. So I've written the inner product with angle bracket, comma, angle bracket. It's often more common to see people write this inner product as angle bracket, line angle bracket, and then here comes the notation. So what does it do? It takes one vector out of your Hilbert space, another vector out of your Hilbert space, and produces a complex number. So I've just changed the notation on you. I said I wouldn't do that, but I actually did do that. I apologize. So actually, why don't we just do it like this? We have a vector space with an inner product. I've used a slightly different notation for the inner product, and there it is. And so here we actually come to the origin of the name. So the name of kets may be a bit odd, but let's look at this thing that I've just drawn here. It's like a bra-ket, right? There's a bra-ket, and there's a C that's been sort of in the middle, which you erase, and then you come up with the notation bra-ket. And so now I'll explain what a ket is in relation to this particular notation here. So a lot of authors will just say a ket is an element of a Hilbert space. That's just the way to understand the notation is that this line angle bracket is, you really should be thinking of that as a vector. In many books, people say that. I don't like that. That's no good. I'm going to erase that straight away. I'm just going to have said it so that you will not be totally like baffled when you look in a book and then the authors define a ket as an element of a Hilbert space. No. That's actually not the most elegant way to think about a ket. Rather, you should think of a ket, of this thing called a ket, as a linear map. and it's a linear map that goes from the complex numbers to your Hilbert space. This is only a teeny tiny difference to defining a ket to be an element of your Hilbert space, but it's, you know, it has a slightly different implementation detail. So what does it do? It's a linear map which takes, what does it do? It takes a complex number Z, and it produces a vector, or the vector, Z, which is a complex number times psi, so where psi is an element of your Hilbert space. So this is really the way you should interpret kets. When you hear the word ket, you're going to hear it. You're going to see it a lot in the next couple of weeks, and probably for the rest of your studies in quantum computation and quantum information theory. When you see this word, think of it rather as first selecting your favorite vector psi, and you should then interpret your favorite vector psi as really just like a vector in your Hilbert space, right? Here's psi. An element of the Hilbert space psi, and a ket is a thing that takes a complex number and multiplies that complex number by the vector. This turns out to be kind of handy. Correspondingly, there is a thing called a bra. So a bra is the other half, right? And what is a bra? It's also an operator. So it's drawn with this funny bracket going the other way. I get complaints from my students that they can't understand my bra and ket notations. So I try and draw it better. So a bra is also an operator, psi, but with the angle bracket going the other way. Where does it go from? Well, it goes from H, your Hilbert space, back to the complex numbers. And it's just the adjoint. It's the adjoint of the ket. And so what does that mean? It means you can, every time you see a ket and you take its adjoint, which we introduced in the previous, then it's really, the bra. And now we are able to identify so this is now connects kets, bras, and inner products. We can identify Z, the action of applying bra and then ket. So that makes they're linear maps, right? You know, so what is a ket? A ket takes a complex number and produces a vector, and a bra takes a vector and produces a complex number. So this thing here is a map that takes a complex number to a complex number. I'll do an example in a second. So we can just define this whole thing as A, right? The action of first doing a ket, then a bra. And so which complex number does it take to which the complex number? Well, it takes Z, your favorite complex number, to the number to a complex number, this. And we typically just define that complex number to be the inner product of the corresponding vectors, psi and phi. So all in all, you can now think of bras and kets. How do I spell summary with two M's, right? So bras and kets are really, you can identify bras and kets with row vectors, or rather adjoints of column vectors. And vectors in H, respectively. Okay, I'll do one little quick example, then explain why we bother with this crazy notation, and then I'll hand over to Michael. So,
Wes, can I just make maybe one or two comments? So when you say vector after the and sign, that's also column vector, right?
That's column vector. Oh, sorry.
Yeah.
You're absolutely right.
And I guess maybe just, I mean, you said this implicitly, but right, if you have a column vector, there's two ways of thinking about it. You can think of it as a vector, or you can think of it as a matrix of size, number of rows times
That's
one.
Right. Yes.
And that's exactly the same that you said at the beginning. If you have a vector, we can think of this as a linear map from a one-dimensional space to the vector space, right? That's the interpreting the column vector as a matrix.
Many thanks, Michael. It's wonderful to have you here to explain that subtle point. Yeah, it's vectors. We're thinking of vectors with kets as linear maps. Yeah, as matrices. Sorry, as matrices with n rows and one column. So it's a really convenient thing to do, as we will see. So I will do a quick example, like a super simple example. So here, this is a vector. I should tell you first of all what is our Hilbert space. Our Hilbert space is C2, so we're talking about a single qubit, and we've got a vector here, 1, 0 inside our Hilbert space. Let's call that one psi. We will typically just write ket psi from now on. We'll identify these two things. So when you see ket psi, you should really think in the background there is a matrix with 2 rows and 1 column in this particular instance. And now we can use the fact that you can take superpositions or linear combinations of other vectors to express our kets in terms of other ones, and this is where the beauty of the notation appears. And so I just chose a wrong notation. I apologize for that. I want to call that 0 ket. So 0 ket is 1, 0, and I'm going to define 1 ket to be 0, 1. And now let's.
I'm sorry, Tobias.
Yep.
If you write it like this now, it's kind of hard to see why you said before we should not see it as a vector in the Hilbert space.
You should see it as as Michael suggested, right? You should look at this vector here as a matrix with 2 rows and 1 column. So it takes a number and produces a vector, right? It's a matrix.
Okay. Okay.
And this notation here is an identification, right?
Okay, yeah, gotcha. Yes.
And so suppose we have our favorite vector inside our Hilbert space, H, psi, so that would be like psi 1, psi 2, we have our favorite vector psi 1 in our Hilbert space, psi 2, psi j, these are complex numbers. Then how do we express this exact same thing in ket notation? Well, we can write psi. It's a linear combination of 2 vectors, namely 0 and 1. So that's psi 1, 0 plus psi 2, 1. Okay, I apologize. That was a slightly awkward notation. So we would change that to psi 0 and psi 1, like so. Now, the beauty of this notation comes when you work with infinite dimensional Hilbert spaces, because when you write your vector elements, with these ket notations, you don't have to write out the full vector. And this is the incredibly important observation about ket notation. So, here I'm working in a 2-dimensional vector space, and you're saying, well, why bother with this notation? Like, vectors are a very efficient way to represent things. But if I have this notation to talk about vectors abstractly, then I can actually take linear combinations of things inside infinite dimensional vector spaces straightforwardly. So, or higher dimensional vector spaces, and then you don't have to write out the full vector, right? Because if you're talking, if instead your Hilbert space was c to the 1000 or c to the 2 to the 1000, right? Then you wouldn't want to write out that vector, because that would take 2 to the 1000 elements to write out. Instead, it becomes incredibly inconvenient to just define ket representatives for elements, for standard elements of this vector space, and then you work with them symbolically rather than as writing out the full vector each time. So it's typically what you have in hand with any Hilbert space is you typically have a basis, and you typically have an orthonormal basis on hand whenever you talk about orthonormal. Command of the tablet is not optimal here. So if you have a when you introduce your favorite Hilbert space, you typically it comes along with a standard orthonormal basis that you can write out. And that orthonormal basis you can sort of describe symbolically as you put a 1 in the first entry and you put zeros everywhere else, and that we'll refer to as ket. I don't know, we'll call that ket 1, for example. We can then talk about ket 2, which represents the vector where you have a 0, then a 1, then zeros everywhere else, and then so on, right? You can introduce this long list of kets. And now, with that definition in hand, you can now talk about much more complex elements of this Hilbert space without having to write out the full 2 to the 1000 element Hilbert space, column vectors. So if you want to, as long as you only consider linear combinations of a finite number of, say, these basis elements like that. So you could certainly write this sort of thing out now, j equals 1 to 2 to the 1000. And you can specify these objects where these psi j's are really just the components of the vector, but now you can specify a finite number of them quite efficiently. And the final comment to make, apart from the notational convenience, is that we can represent matrices and operators very efficiently this way using so-called ket bras. So a ket bra is, as the name sort of suggests, is a concatenation of a ket and a bra. So I write them like this. Now, everyone who sees me do that says psi x phi. Nee. So what that really, you're going to get used to my notation on this. This is psi, ket, then concatenate. So that dot means concatenate with phi. So this symbol now has a meaning. You can interpret that as a row or an adjoint of a column vector multiplied by a column vector, and that's a matrix, right? The rules of matrix multiplication allow you to interpret rows times vectors as matrices, and you can now take any operator and represent it as a linear combination of ket bras. So this allows you to represent any operator as a linear combination of ket bras. And I'll do one example and then I'm done. Okay. So we'll just go back to our Hilbert space example of a qubit. And now we have an operator on a qubit. What's an operator on a qubit? So an operator on a qubit is a matrix, and a matrix takes an element of the Hilbert space to itself. In our case, it's a 2 by 2 matrix like this. So it's M11, M12, M21, M22, right? I've completely specified the matrix now, where each of these M's, J, K's are elements of the complex numbers. And now using this ket bra notation and this standard basis notation, so I'll remind you of the standard basis. The ket 0 in this particular instance is 1, 0, and we have 0, 1. We can represent this matrix here as a ket bra. M is M11, 1, 2, just makes life easier. M11 is 1, ket bra 1, 1, plus M12, 1, 2, plus ket bra M21, 2, 1, and finally M22, 2, 2. So operators can also be similarly expressed as linear combinations of ket bras in the same way that bras can be represented as linear combinations of bras and so on. Now, that's effectively all I want to say about this notation. At the beginning, it's an extra work for you to work with this notation. You're like, vectors are better, matrices are better, they're more explicit. But now that you've seen the notation, I encourage you to try and convert normal vector operations into this notation. And then as you gain more experience in working with quantum mechanical systems, you'll start to see the virtue of this notation. And that virtue I can't convince you of until you've had to work with high dimensional vector spaces. So that's something where you'll slowly appreciate the virtue of the notation. But I don't believe at this point I can declare that it's a better thing to do. So I think that's the moment where I would like to stop talking and open for any questions before I hand over to Michael. Okay, it doesn't seem like I have any questions. Yeah,
yes.
Leah?
When you introduced this, you wrote this row vector multiplied by the column vector.
Yes. Yep.
I cannot see why this does not give only just one number. For me, this looks like a linear combination. Like,
oh, thank you. It's good that you asked that question.
It's the other way around, right?
Yeah. The other way around.
I thought so.
Oh, Mom, I apologize.
Waiting for a good moment.
There you go. See?
Sorry.
That's why questions are good, man. Because
Okay.
I wrote total nonsense. There you go. That's what I should have written.
Being used to writing these scalar products so much, right?
Yeah. Yeah. Good. Okay. If there's no other discussion points, questions, then I will stop sharing and then I will hand over to Michael, who's going to give us the first taste of quantum information theory. Now, Michael, can you share your screen or is that not?
Yeah, let me just try. 1 sec.
Oh yeah, that works now. Beautiful.
This works, right? You can see my screen wiggling about. Can you see my screen?
It looks perfect.
Awesome. Cool.
Thanks. All right then. Well, introduction. We all met each other many times in our introduction sessions, but it's really a pleasure to introduce Michael to you right now to give this first taste of quantum computing, because Michael has had significant experience in the past years. He's really one of the leading quantum algorithm developers worldwide. And he's had significant experience actually teaching quantum computing to a wide, diverse audience. I think that's fair to say, right? And so I'm looking very much forward to your introduction.
Great, thanks Tobias. Yeah, hi everyone. Great to have the chance to also talk to you in this format. Let me just rearrange all the screens. Fantastic. Yeah, please interrupt me at any point with questions. So I guess I wanted to give you sort of a gentle introduction to quantum computing. I probably prepared more than what we have time for, and I think it's more important to focus on the concepts and take things slow, also for myself. So I'm sure there will be time to continue at a future date, so we don't have to get to any particular point today. But what I want to discuss is basically, give you sort of a flavor of, what do quantum algorithms look like, and a simple example where a quantum algorithm does something more efficiently than a non-quantum, or how we say a classical algorithm. So that's the plan for today. Before that, maybe though, I'll just take the opportunity to play a little bit around some more with these kets. So just make some comments on what Tobias was saying. Sort of, I studied pure math, so I think it's okay if I say that, as it's completely fine to think of kets as vectors and as bras as covectors or as row vectors. It is very nice from a conceptual perspective to think about them as functions, as linear functions, the way Tobias described. And it's actually something like I was also saying before, we automatically do, right? If you see a grid of numbers and it has it's a single column, in our heads we all the time switch between thinking of this as a vector, depending on the context, or as a matrix, right? Somehow that's not even a difference for us. Usually we don't even think about that. But if one writes it down mathematically, then one arrives at exactly what Tobias was explaining before. I guess the way I think of these kets is also, and I think also in many papers that you maybe have looked at or will look at in the future, you also just see people basically using this notation and just putting some arbitrary label in the middle. Okay, so they may, for example, write, I don't know, maybe in a classifier they would just write ket nice. Okay, so that's just a vector. We call it the nice vector. It corresponds, to some vector, but it doesn't matter what it looks like, right? It's just important that we gave it a name. Okay, so that's one comment. So in particular, Tobias explained, that usually when we have a qubit, we have the ket0 vector and we have the ket1, and I will write equality signs, not tildes, because for me they're really the same thing. But there's another, so those two vectors of course they form a basis, right? So like Tobias was explaining, any vector can be expanded as a linear combination of those. But of course, there's many more bases of C2. And there's another basis that's very popular. It's sometimes called the Hadamard basis. It looks as follows. There's the 1, 1 vector, and then we normalize it to have norm 1. And the 1, -1 vector, right? You see that the inner product between those two is 0. So they are orthogonal. They also have norm 1 because they divide by 1/√2. And this basis, as I was saying, is usually called the Hadamard basis. Hadamard basis. This is called the standard or the computational basis. And we'll see that actually it's very powerful and something that we cannot do with an ordinary bit, that you can switch between these bases. In some sense, that's where all the magic of quantum computation will come from. Now, why do I talk about this now in the context of this ket notation? The reason is that we also use this funny ket notation and this very standard way for denoting these basis vectors. Usually this is also called the plus-minus basis. So what we would do is we would take a plus and put a ket around it. And we would take a minus and take a ket around it. Now, where does this notation come from? Well, because this vector is 1/√2 times ket0 plus ket1. And the bottom one is 1/√2 ket0 minus ket1, right? So the label here sort of focuses on the important part. Do we take a superposition with pluses or one with minuses? So I hope that this gives you a little overview of this ket notation, sort of in a very practical, from very practical perspective. So please do ask me right now if anything is unclear, if I made a typo on the slides. So just to follow up on that ket notation, two things happened. I just recalled the ket notation, and I also introduced a new basis that I think Tobias hadn't introduced before. And of course, there's many more bases, but these are the favorite ones for today. Maybe another sort of, you may not yet be convinced that this ket notation is a useful thing. Why do we write ket0? There's good, we already heard lots of good motivation for it. Another one that I personally like is, Tobias mentioned ket0, ket1, they are bases, right? So if you're a mathematician, probably you write your basis as E0 and E1. Right? That's like a very standard notation for a basis. But it's a bit weird, right? Because somehow there's a lot of baggage here that's completely unimportant, namely the letter E. It's the same every time. And the important part, which is the 0 or the 1, it's a subscript, right? So in this ket notation, it's really focusing on the important thing, the label, and then it's sort of decorated by the ket or a little flag around it. Okay. So that's maybe another way to motivate this notation. For me personally, now having worked on this field for a while, it's also really useful to see at an immediate glance what type of object I'm looking at. When I see a ket, I know it's a vector. When I see a bra and a ket together, I know it's a number. That's maybe more complicated if we would write it, in a more mathy way with whatever, kind of just symbols and little stars without having the flags around it. I guess this thing maybe doesn't syntax check, maybe it does. You will not discuss it. Okay. Cool. Okay, so these were just 2 comments. Maybe one more comment to practice this bra-ket notation one more time. Tobias explained we can also take these outer products, right? We can write ket times bra, and that corresponds to an operator or to a matrix. And he has written down, for example, something like that. Does anyone want to? Do you know what kind of object? Well, that thing is not. It's a matrix, right? It's a matrix, as Tobias explained. Who wants to say what the matrix looks like? Maybe you remember from the first part. Any volunteers? So imagine so we work with a qubit, so this should be a 2x2 matrix. What would that particular matrix look like?
This would be 1, 0, 0, 0.
That's right. Thanks, Timo. And this would be 1, 0, 0, 0. Now this matrix is not an arbitrary matrix. It has a bunch of interesting properties. It's rank 1. Okay, so in rank 1, it not only has rank 1, it's also a Hermitian matrix, right? It's the same as this Hermitian conjugate, and it actually squares to itself. Okay, so that means actually this ket 0 bar 0, it's a projection matrix. What does it project on the one-dimensional subspace spanned by this ket 0 vector? Another way to say it is if you apply this matrix to ket 1, it just gets annihilated. Okay, nothing comes out. Right? So 1 0 0 0. If I apply this thing to 1 0, I just get 1 0 back. But if I apply it to 0 1, I get nothing. I mean, this is now not ket 0, but 0, the 0 vector, the vector of length 0. Or maybe I could also write it like so. Okay, and so that's in general, that's a general fact. Whenever you have bra psi, ket psi, this object sends psi to itself, and everything that's orthogonal to psi is sent to 0. So this is always a rank 1 projection. I think that's it's a very nice way of writing a rank 1 projection, right? Not as a gigantic matrix, not as some complicated way. So you can immediately pattern match whenever you see ket psi, bra psi, that's a projection onto a vector at a one-dimensional subspace. Okay, very useful. Any last questions about this bra-ket notation before we sort of zoom out from spend the rest of today actually not discussing notation, but concepts? I'll just have a sip. It's actually a nice exercise maybe for you to think about, and you can ask me about it to verify that this is a projection, whatever vector you, well, whatever unit vector you put in. Okay, very cool. So do remember the spaces. It will come back perhaps today. Chandra, for how long should I be going? So I think I think Tobias meant to be done a little bit earlier, but I think we spent lots of good discussion actually. Should I stop at 4 or 4:30? What's the?
I mean, 4 would be really short because that's like 15
Right.
minutes.
Exactly, yeah.
What I mean, you should have a feeling like what's a good.
Yeah, I think 4:30 should work well.
Yeah.
Great.
Yeah,
I
try-
think
before the audience.
4:30 seems. I mean, we had a soft start, so it's not like we're
Yeah.
spamming
Yeah,
you
but
with information.
I think 4:30 is enough because then people start to get tired.
Sounds good.
When
I mean,
you
in some
see
sense,
when you see me going
something-
into this position, you know that. Yeah, it's time.
Yeah, I mean, something would also be I'm not sure if we had breaks before, but this would also be an optimum moment to have a 5-minute break because now actually we start from scratch, but maybe we had such a soft start that I should just keep going. So maybe if you would like a break, you can raise your hand, and if I don't see hands being raised, I will just continue. So another way. Very good. Everyone seems to be eager to learn about quantum computing. So that's fantastic. So let's get started. What we'll do, well, actually, it will take us a while to actually formulate a quantum algorithm because we first want to talk about some computer science concepts. Okay, and so I'll want to start from the very beginning. Okay, what's the goal of algorithmics and complexity theory? So I mean, one central goal, right, is to solve computation problems, and then we have to say, okay, what is a computation problem? We don't want to solve them in an arbitrary way, say by writing down formulas, but we want to solve them by algorithms, and we want to find algorithms that solve these problems as fast as possible. Okay, maybe we won't even know how fast can that be done. So I'll take the time to write that down. Okay, so in CS, computer science, we want to solve computational problems. By algorithms. Yeah, and just colloquially as fast as possible. And of course, it's not clear what all of these words mean. Of course, many of you will know, they will have some preconception. What's a computation problem, right? Is it to find something? Is it to show that something exists? There's many options, right? Is it to prove a theorem? I mean, all of these are valid answers, but they correspond to different kinds of problems. It's also maybe not so clear what an algorithm is. Is that a Python script? Is it something written in pseudocode? Is it a Turing machine that's programmed in a certain way? Is it a circuit? There are interesting nuances between these or differences between these concepts. And then the last point is the notion of fast. Okay, I wrote fast, not efficient, because efficient sometimes has technical meaning. Fast can also mean many things, right? Efficiency is a more general term, can also mean many things. Can be using little time, using little computational resources, lots of options. And it of course depends on the model that we look at, okay? So that's sort of the space in which we're going to work, and I'll try to make these things very concrete as we move along, give lots of examples. And the goal of hopefully today, if not next time, will be to give you a bunch of simple computation problems. They may look rather contrived, but we'll sort of start with very contrived ones and then move towards actually very practically interesting ones, very general ones. Simple problems where quantum algorithms can really rigorously give an advantage. So where we can understand that and why they work faster than any possible cluster algorithms. Okay, and making that precise, that's going to be the goal, making that clear. So today, let's go. Hopefully today, yeah, simple problems where quantum algorithms, and I always write Q and not quantum, give an advantage. So that's sort of a first attempt actually at what we want to do today, and we'll be able to phrase it more precisely in a moment. Okay. So first question, okay, and the quantum part is of course important. So first question maybe that you might ask, and I think that's something you have not discussed yet, is actually what is a quantum algorithm? What does it look like? So I think you have now a very nice introduction to the laws of quantum mechanics, the axioms of quantum mechanics. Know this ket notation, what gates are. Tobias, I think, also explained measurement, I'm sure, as a notion, what happens when you measure qubits. So all these building blocks, but what is an algorithm? So that's maybe the first question I want to discuss. So question, what does a quantum algorithm look like? And I don't want to give you a very mathematical definition. I want to draw a picture and make some comments about it. Okay. So that's the first question. Oops. Okay. So it turns out that in quantum algorithmics, quantum computer science, we usually like to think in terms of circuits, which is something that seems very low level and very maybe unfamiliar, for those of you who have been in a classical computer science class. Although if you have been in such a class, maybe you think back, and probably what you did is you did learn about Turing machines and states and transitions and automata and so on, and those are also very low level if you think about it, right? And a lot of this low level is, of course, because we encode, things that we weren't reason about, integers, for example, in some binary fashion, and then we compute using logical elementary operations and so on and so forth. So the same is true in the quantum realm. And for us, it turns out to be more convenient to think about circuits. Okay, so what does such a circuit look like? So we start out with a bunch of qubits. Okay, we all initialize them in this 0 state. So for me, the lines are horizontal. There will be horizontal wires, like in a circuit. Each wire corresponds to a qubit, and they all initialize in this ket 0 state. Okay, so that means that the whole Hilbert space, which is C2, tensor C2, tensor C2, lots of C2s, is in a state that's ket 0, tensor ket 0, tensor ket 0, and so on. Okay, so there's little tensor product signs, but usually we don't draw them. Okay, we don't denote them. So it's basically saying I'm initializing my memory, my quantum memory, all in a 0 state, except that our ket around it because it's vectors. It's a vector Hilbert space. Okay, and then we apply these gates, and these gates, as Tobias I'm sure explained, are unitary operations that act only on a handful of these qubits at a time, usually 1 or 2. Okay, so for example, maybe there's a gate that's applied to these first 2 qubits. Maybe at the same time we apply a gate on the next batch of 2 qubits. Maybe then we apply a certain gate between the second and the third one, and maybe this is a controlled NOT operation, which you may maybe have seen this notation being used. If not, I'll just tell you, and we can come back to this. So this is also in classical computing a standard way of denoting controlled NOT. So that means you flip this qubit, if this qubit is in state 1. So there's a matrix corresponding to this, the C0 matrix. Is that something Tobias explained? Tobias, did you talk about it?
I covered awesome. C0.
I should have really watched the video. I apologize. Then I would be up to speed with that. Fantastic. Okay, very good. So we continue, right? And then at some point, usually at the very end of the algorithm, we measure. Okay. And I'll denote this by such a picture. Maybe we measure the first qubit, maybe measure many qubits. Oh, sorry, this is terrible. So this should be a little dial. Okay, the dial kind of doesn't make sense because the answer is either 0 or 1. It's not actually on a scale, but okay, we usually like the symbol. So the outcome of such a measurement is an ordinary bit, 0, 1. Here I measured the first qubit. I could also measure more qubits. Okay. So there's these sort of 3 phases, but of course you could continue afterwards. You could say, okay, I measured this qubit, I got answer 0. Because I got answer 0, I'm now going to play another sequence of gates to the other qubits, then I measure and so on and so forth. But in the most simple setting, that's what a quantum algorithm might look like. So there's a phase that's trivial where we just initialize all the qubits. Then there's a sequence of gates that we apply. So we apply gates. And finally, we measure 1 or more qubits. 1 or more qubits. Okay, and then we interpret the result. Okay. So that's sort of the anatomy, if you want, of a simple quantum circuit or algorithm. Maybe I'll say we usually use circuits, consider circuits. This is, yeah, sort of the anatomy of simple quantum algorithm or quantum circuit, the way I wrote it. But I want you to think of this as an algorithm, because what I imagine is that these steps, they're being done by some control program, by some, so similarly to if you program a graphics processor, for example, or another kind of co-processor, right? There's sort of a main program saying, and it's saying, now execute this snippet of code, now execute that snippet of code, and in the end you read back the results. That's roughly speaking how GPUs were programmed 10 or 20 years ago. So here it's very similar, right? You have a quantum processor, it's sitting somewhere in a fridge, and we program it. You say, okay, reset the quantum computer, apply this gate between the first 2 qubits, and so on and so forth. And at the end, you do this, okay? And now this ordinary computer that controls, that of course may select a different circuit depending on the problem size, right? If you have, of course, if you want to manipulate very large numbers, then you need more qubits than if you have a small number to work with, and so on and so forth. Okay, so what I imagine usually, I mean, there's many ways of thinking about it. I imagine that this kind of picture is sort of controlled by an ordinary computer. And when I say controlled, I really mean that, the sequence of what is supposed to happen on the quantum machine. So what I wrote below, what I wrote below, that's what's supposed to be controlled. So these kind of things. Yeah, similar to GPU world, and that the circuit that we actually run depends on the problem size. Okay. Hopefully this will become more clear, but you can already ask me now if you like. Okay. So, but it's sort of clear, right? If I want to sort a list that has 1,000 elements, I probably need, maybe 1,000 qubits, or 1,000 times something many qubits. If I have a list with 1 element, it can be a smaller circuit. So that's the way to think it. Leah, please go ahead.
Like I have not really any idea about how like normal computing works, or not quantum computing, let's say, but I cannot really see from here why should it be different from not quantum computing, because also in classical computing you have like some initial things, some gates, and then something comes out, right?
Perfect. No, you're completely right. I could have given the same picture to explain what a circuit is, what the circuit model is for ordinary computing, and it would have written exactly the same. And the only difference is these little cats here that make it clear that, so in an ordinary computer, right, the state space would just be a bit string of length 1, 2, 3, 4, 5. In our quantum computer, state space is very different. It's now a state space with a C2, tensor C2, tensor C2, tensor C2, tensor 1 last C2. Okay, so that's on our quantum computer. And on a classical computer, right, it would be bit string, so 0, 1 is a single bit to the 5. So that's the only difference. Well, that's the difference in the state space, and then another difference is in these operations that we're going to do. If all we could do is this controlled not, for example, then everything would stay classical. We would always have basis vectors, and so essentially we would be working with bit strings. But since we can do other matrices that create these superpositions, the states that are going to be created by such a quantum computation can be very different. And it's sort of, we have to understand how to make use of that.
So the important thing is that these gates might create superposition, what you cannot have with regular bits.
That's correct, yes. So if one precise way of saying it is, so these gates, they correspond to unitary matrices. If these unitary matrices would always be permutation matrices, so single 1 in each row and otherwise zeros, then they would just map basis states onto basis states. And so essentially they would just, always have, there would always be a single bit string at each point of computation. We would not gain anything. Yeah, so it's a great question. You could also say, oh, how about probabilistic computing? If you can introduce randomness, the same picture and the same words I said would make sense, but now the state space would be neither of these two. It would actually be probability distributions over bits, which is, you know, something like that, but with positive entries.
Okay.
And normalized in a different way. Instead of the square summing to 1, the entries would sum to 1. That makes a huge difference, it turns out. So somehow we'll see, we will have to see in a moment why the minus signs that we can basically create in our states, why they make a difference. Yeah. That's the key. Yeah.
Thank you.
Thanks for the question. Very good. But now, I think we're on board what the circuit/algorithm looks like. So this is a circuit, and these circuits are generated, or we can imagine them being generated by an algorithm, and we usually identify these two things. Okay, having in mind that so it's really a family of circuits we're reasoning about, one for each side of the problem. Okay. The next question maybe that we want to discuss is how does such an algorithm get its input? Okay, so usually in a computation problem, there's an input and an output, so a problem that you want to solve. Okay, so how do we model an input? Okay, so one way of modeling the input would be we just initialize part of the computer with the question that we want to, the problem we want to solve, the problem instance. Okay, I'll give you a bunch of examples in a moment, but one example would be, suppose you want to factor a number. Okay, then you want to put in the number at the beginning, right? I mean, or somewhere you want to put in the number that you want to factor. The algorithm has to learn of its input. And there's actually more than one obvious way to do that. And I want to motivate this by a bunch of examples, okay? And then I want to basically make a distinction between what we call black box or oracle problems and ones where the input is given explicitly. And that turns out to be a very important distinction. Again, that's a distinction we also make in ordinary computer science, but in our context, it will be very interesting, okay? All right, so second question we want to discuss, therefore, as I was saying, is how does an algorithm get its input? How is the input specified? How is input specified, maybe? And it's sort of related to that, as it will turn out, is how do we quantify actually, when I say quantum algorithms give an advantage, I have some measure, some quantity in mind that you know is sort of better for a quantum algorithm than for a classical one. So I want to discuss in correlation to the first question, how do we quantify the advantage posed by one algorithm over another. One is one algorithm faster than another. That's basically what I want to discuss. Okay. And the discussion that we'll have will sort of correlate these two questions. Okay, but we'll start with the first one. Okay, how is the input specified? And I just want to give you a bunch of examples. I want to give you something maybe I should call a computation problem, but I'll call it a task, which I think of as a more informal word, because for me, a computation problem is something that's precisely defined. There's an input and a desired output, and I say the input should be a bit string encoding a natural number, something like really precise and rigorous. When I say task, I'm just going to write, sort of sloppy words. So I want to discuss with you a bunch of tasks. So there'll be a little table that we'll create. And for each task, I want to discuss how could the input be specified? What would be natural to specify the input? Okay. So one task I want to discuss is the task of factoring a number. So if a composite number, we want to figure out a factor. Okay. Closely related problem would be to determine if a number is a prime number or not. Okay, if it's a prime number, it has no interesting factors. Okay. So here, it seems like the input is very obvious. It should just be a number. Well, it should be a number. We have to encode this number somehow, right? Because even for ordinary computers, and the whole discussion, by the way, that we'll have now, well, you can ignore quantum for a moment. Quantum will come back in full force later, but we're just talking now about problems, not about solutions. Okay. So the way we specify the problem, we just think about ordinary computers. Okay. So we want to specify a number, and usually what we would do is we would write down the number in some system, say in binary. Okay. Turns out it doesn't make a difference whether you specify numbers in binary or in decimal or whatever. Binary is nice because then we use zeros and ones. It would make a difference if we specified our numbers in unary. So unary is, like one tick for each, if the number is 1,000 ticks, 1,000 ones. Whereas, if you do binary, you need roughly log 1,000 bits to specify the number. So this logarithm is, of course, a radical difference. But okay, I think that's very, I'm not even sure why I talk about this, because I think this is very clear to you anyways. So we would specify a number, so that's the input here, in terms of its digits, and maybe we pick the digits binary, just to make life simple for our computer. Okay. So this seems very, so I'll put a question mark here, but really maybe it should be exclamation mark because I'm not sure what else we should be doing. Okay, so that's one thing. Here's another task. Suppose we have a function, that's an optimization problem. We have a function, maybe a convex function, we want to minimize it. Okay. So the input here in some sense is this function, right? So given a function, I want to find a minimizer or minimum or the minimal value. What do you think would be a natural input here for such a problem? Maybe someone has thoughts. You can also write in chat, by the way, if you don't want to speak up. So the computation task is an optimization problem, a minimization problem. Given a function, minimize it. Now it's maybe not so obvious how to specify such a function, but maybe you have some suggestions.
Well, the easiest way would be to say just a linear functional.
Mm-hmm. Very good. So you could say we can specialize we can say instead of looking at a completely general function, let's focus on a specific kind, which we can somehow encode in a natural way.
But
that's
we
what you
chat as well as a kind of circuit, says Philip Kelvin.
Yeah, that's right. So that's also a very nice suggestion, right? We could provide a circuit. So I'll write all these things down. So we could restrict. Well, let's say suppose our function, if linear, then just as a vector, right? Because then would be sort of a dot x, and we just specify the vector. If it's a general arithmetic function, we could, well, if it's a general function, we could specify it, for example, an arithmetic circuit, or by, say, a formula, right? These are very similar things. So this is one way to do it, okay? Does anyone have another thought? How else could I specify it? Imagine you implement, in in Python, you implement gradient descent. How would you specify the function that you want to minimize? You want to implement a minimizer, okay? In NumPy, for example, right? Maybe some of you know NumPy. There's a minimization function, maybe it's SciPy, I forget. How would you?
Computer program?
Sorry, say again.
As a function, a computer program?
Yeah, exactly. So usually what we do is you sort of give a callback function, right? So we feed our minimizer actually a function. And well, the minimizer knows nothing about that function except how to evaluate it, right? So sort of we pass a black box, a callback, or closure. I mean, there's lots of different terms for this in computer science, depending on the community. So that's another option, right? So we basically pass it a black box. And so this, we can imagine it's sort of a gadget. We put in a possible value of x, and out comes f of x. Okay, so maybe I'll write f into this box. Okay. So that seems like a very different way of encoding the problem, right? Now of course, it's very cool, right? So it's like a very general way. You don't have to restrict to linear. You don't have to restrict to formulas. It's a very different input model. Okay, you just have access to the function, and you don't know the function in its totality unless you ask it questions, unless you put in x value. Right? Any x, you can draw an f of x, but not more. Okay. Maybe in the context of gradient descent, it may also be actually natural to give black box access to the gradient instead of the function itself, but that's sort of a detail. Another way to think of it, of course, would be, given such access here, right, you can compute the gradient by finite differences, and then you could, for example, do gradient descent, right? So that would be a natural way of doing it. Does that make sense to everyone? Does anyone have a question about what I mean when I write something like this? Right, so the idea would really be, right, I have a little Python snippet. Oh, let me see in chat. Oh yeah, exactly. Sorry, Philip, I only saw you. Oh, exactly, black box function. Yeah, right. You do like a little def, gradient descent Python thing, and then you just pass f as a function, right? And then somewhere inside your gradient descent routine, maybe you do a bunch of gradient steps, and then you would actually numerically estimate the gradient by calling f of x plus epsilon or something like that, right? So that's kind of the idea. So do you have any questions about what I mean by a black box function? Okay, it's really a gadget. You put in x, you get out f of x. And it seems extremely natural for the problem we're discussing here. Here's another computational task, finding an element in a list. It's a little bit underspecified what I mean by this. Maybe the element could be 5, the number 5. Maybe the element could be something that satisfies a certain criterion. I don't want to worry about that part. What I want to worry about is the list. Okay, how do I, provide a list as an input? Okay. And again, there's two options that you could imagine. One is, well, maybe the natural one is, suppose it's a list of numbers. Well, we just list each element after the other. So if the list has 1,000 elements, 1,000 contains 1,000 numbers, the input contains 1,000 parts, and these parts are the first number, the second number, third number, and so up to the 1,000th number. Okay. So the one option would be a list of, say, elements, say numbers, one after the other. But again, there's also a natural black box model, right? And what would that look like? Well, it would be a database, right? So basically, you would input a location, say, I want to know the ith entry in the list. So you put in I, an index, and what comes out is, well, the ith element of the list, say the ith number. This would be sort of a black box way of specifying a list. Okay, and you can really imagine it's like a database query, right? Or a table query. It's like, a gigantic Excel sheet, but instead of someone handing you over the Excel sheet, as a document, you say, tell me row 1,000. Okay, now tell me row 200. Okay. So there's a famous algorithm called Grover's algorithm, which is about finding things in a list. And there, indeed, this is the right model that we'll be using. Okay. So why would one like to consider such a model? Okay, and not this explicit one? Well, in some sense, this is very general and abstract, right? Because now this black box can be implemented in an arbitrary way. It could make a call to some server. It could run its own little quantum algorithm inside. It doesn't matter, right? Some box, it gives you the ith element. So if you can provide a quantum speed up, for example, for the search problem, for this finding problem, in this domain, you can apply it whenever you want to find an element in some unstructured list. Okay. And so that's sort of one point. Okay. Another point is, of course, suppose you specify this list one element after the other, then even just to read this entire thing, right, it takes a lot of time. So yeah, go ahead, Sandra.
Michael, just I think this is a really, really, really important point, and to just encourage everybody who's listening. I was really struggling with this for quite a while when I first encountered it, because in classical algorithms, when you do these kind of things, for instance, an online algorithm, there's a typical thing where you have these, you need to make a choice between some things, and it's always going to be the last thing you look at. That's sort of the worst case. So when you think in this classical way, and you look at the left option that you're giving here as the input, you look at this and it's like, how could you ever beat this? This is impossible. So looking at this on the right-hand side, and of course, the way this is typically stated in literature, it's searching a list. It's just plain wrong. I mean, yeah, mentally wrong. So
that's right. Like it's only right if you have this interpretation in mind, and not the obvious one. Indeed, yeah. And I mean, sort of, you're not meant to understand Grover's algorithm at this point. At this point, I just wanted to discuss that there's even another option of thinking about the problem.
Absolutely.
Namely this black box one.
And I'm just jumping in here so people like put that pointer into their mind. Just when we get to Grover and you say like, how can this be? This image that Michael puts up there, it is very different, and it is not looking into a list. It is you have this overlaying black box function, which is why you can look in multiple places at once, and because
that's right. Yeah, and of course, I mean, there's more magic. Like you're already anticipating what comes, right? I mean, we have to. I mean, I think these pictures hopefully are very clear to you, but of course now if things become quantum, it's not even clear what these boxes should be doing. Okay, and we'll also discuss that hopefully still today.
So anybody who's listening here now, later on, it's not you hear it once and it's fine. You just remember this point.
Yeah, please do ask questions as well. Yeah.
So
I want to.
Can you hear me?
Yes.
Does the quantum computer have to be able to evaluate the black box in this quantum way, right? Or
yeah, I mean, I think you have something in mind that I haven't even mentioned. Maybe someone else has already spoiled a surprise for you. So we will have to talk about what does it mean to be. So these kind of black boxes we usually call oracle. okay, and evaluate and calling them as we call querying an oracle. And we have to discuss what that should actually mean in the quantum world, okay? And I want to discuss it very carefully in a moment. So there will be a quantum version of such boxes that seems more powerful than the classical box, the boxes that we've been discussing so far. And I want to argue to you why, nevertheless, this is not a cheat. It makes a lot of sense. But I think this will maybe take us time. Hopefully we can do it today. But I think it's a very good discussion to have. Yeah. So, I mean, maybe allow me to postpone that question. So
sure.
But I mean, from a high level point of view, it's the same as in the classical routine, right? If you, in your Python program, you write a gradient descent minimizer, that gradient descent minimizer just gets, this f, this function you want to minimize, and it can call it whenever and however often it wants to call it. Similarly, for a quantum algorithm, that will be the same. Our quantum algorithm will call these quantum oracles, these quantum black boxes at various points in the algorithm. And maybe we are interested in how often do we call the box. Okay, maybe that's how we measure complexity. Or maybe we do it in different ways. So we'll discuss about this in a moment. I mean, maybe what I want to do beforehand though, is just to discuss two more examples where again, maybe there's two natural choices of input. So the explicit model and the black box model, just to get everyone on the same page, if that's all right.
I'm sorry, I'm not sure if I missed that point, but I didn't really get why you call that black box. Is that because you don't really know what this function does, or?
That's right. So the algorithm, the only thing the algorithm knows is, okay, there's a function, and well, it's a function, so you can put it, you can ask it in some sense. You can put it x into the box, and the box says, oh, f of x is, well, it's the value of the function. But we call it black box because it's not like we get this function as a big function table. Okay. So you can think of it as like an interactive thing, right? I have a function in my mind, and you want to know about the function. One option is I just tell you f of 0, f of 1, f of 2, f of 3, the whole function list. Now you're informed. That's sort of the left-hand side column. The other option is that I say, okay, I'm a function, and now you get to ask me questions. You can ask, hey, Michael, what is f of 0? And I tell you, okay, it's 5. Then you say, okay, maybe now I'm interested in f of 7. Okay, now I tell you another. So that's the model, okay? So for example, when you minimize a function using a gradient descent, maybe that's something you have seen, then kind of the only thing you need to know is what is the gradient at a certain point, but you don't have to know if the function is linear, or if it's quadratic or whatever. So kind of the only thing you have to do is you have to say, hey, function, tell me your gradient at point X. And then you know the gradient, you do a little step, you update, now you get a new point. Now you say, hey, function, what is the gradient at this new point, X prime, and so on and so forth, okay? Yeah. So the algorithm is completely agnostic of the inner workings, but of course, if you want to now analyze the algorithms, we do have to know maybe it's a convex function, it's a linear function, it's a Lipschitz function, and so on. Okay. Chandra, I think you want.
Can I just add a picture to this? I cannot draw on yours, but suppose I give you this, right? Here's that interval. Okay, you see that interval? And now all I'm telling you is that above this interval, there is a function, and the only thing I'm telling you, it's a convex function. Yep. So now I let you, and these arrows indicate this. You can sort of check and say like, okay, what is the value of the function of this? Now Michael was saying you could look at the gradient and so on, but how do you get the gradient? Maybe we'll just more elementary here, okay? And now what is above, you don't know. So here's a bunch of functions. They could all be possible convex functions, right? So the black box thing means you say, okay, I give you an x, tell me f of x, and then I'll tell you this, and maybe you have the f of the boundaries as well, okay, like you know this, but so there's a bit more that you know now. And now if I give you maybe, and you say like this, well, a convex function. So now you have guessed this one here. You look at this, right? So now you know these 4 points. And because of these 4 points, you can say like, oh man, I don't even know what the curve is, but I already know that because it's this, it cannot be in this interval.
Yeah, like because it's convex, so it's going to get something above the function in this way and so on. Yeah. So
this is golden search classical algorithms where you take a sequence. Golden search means that golden ratio does good things and so on and so on. Think about this for yourself a bit. You get to ask these x's. You say like, tell me f of this one, and that one, and that one. And now you get to determine this sequence here, and you want to narrow down where the minimum can be by depending on the answer that you get. In a classical setting. When you put your mind around this, then you get into this frame where you say like, okay, it doesn't matter what the how this F is computed. And now I hand it back to Michael.
Yeah, exactly. So I mean, I'll give you two more examples. I mean, something that also came to mind, right? This is sort of guess a number game, right? Maybe I imagine a number between 1 and 100, and then you can ask me questions. You know, I don't know, is your number 50 or something? Then I say no, it's smaller. No, it's larger. Or yes, it's that number, right? Then you can sort of zoom in this way. So this is also kind of, it's a bit like an interaction, right? And then somehow the questions, how few questions do you have to ask me to figure out the right number? That's kind of one way of thinking about this computation problem. Different one would be if I just tell about, it's not even clear. Right? So somehow the black box is hiding something you actually care about. Could be this minimum. It could be I don't know, the element in the list, like in my example, and you want to figure out by sort of interrogating this black box or by using it, as a subroutine if you want, in your algorithm. I'll give you two more examples. One is sorting a list. That one's kind of interesting, I think. And the last one is solving a linear program. We'll do that in a moment. So sorting a list, right? Of course, we already discussed how to specify lists. So this is a good option. That's a good option. So I'll write C above. But here, there's also another natural way to do it, because just imagine you want to sort a list, right? So maybe it's a list of numbers, maybe it's a list of names. In some sense, you don't care what the elements are. In order to sort a list, the only thing you need to know is a certain element larger or smaller than another one? Okay, so only the order is important. So you could imagine in this case a black box that you specify I and J. There are two positions in the list. And the answer is, for example, say it's 1 if xi, so the ith element of the list, is larger than xj, and 0 otherwise. Imagine they're all distinct elements for simplicity. Okay, so this would also, right? So this would be a way of allowing you to. That's enough information to sort the list. Basically, for any two elements in the list, for any two locations, I will tell you this one is larger than the other, or this one is smaller than the other. And then you could ask, how many of these comparisons do I need to make to sort a list? Okay, so that's actually how in theoretical computer science one studies, complexity of sorting, and how one shows, that n log n is, required. So maybe that's sort of another example. And so why is this interesting? Because you don't have to worry what's the type of the elements, or maybe you have a list of data, but you want to sort there's many different criteria that you want to use. Maybe you want to sort by first name, by last name, by phone number, and so on. Here, you don't have to worry. You just specify such a comparator function, a comparison function that just allows to compare two arbitrary elements. Okay, and again, it's in a black box fashion. You don't actually need access to the list. You just need to know, given I and j, is the ith element larger or smaller than the jth element? Okay, so that's one example. And then the last one I wanted to mention, that's a bit more abstract. Maybe it connects to some things you have discussed with Shandor. So I guess you guys discussed linear programs as a paradigm somewhat. So a linear program, there's many ways of setting it up, but one way to do it would be, suppose you want to minimize a function, a linear function, so c dot x or c transpose times x, subject to, I'll just say ax large equals to b. A is a matrix, little b and little c are vectors, x is a vector, say in Rn, and this larger equals means component wise. Okay, there's just a bunch of linear inequalities, and you want to, so kind of you have a set of x's, right, that satisfies a bunch of linear inequalities, and you want to minimize the linear function. Okay, the details don't matter so much, but the general flavor, it's a minimization problem, and it has constraints. Okay, so how could you specify such a linear program to your linear programming solver? Okay, the obvious way, well, it's just we have a, b, and c, and we just specify them as arrays of numbers. It's arrays of numbers. Okay, that would be maybe the obvious choice. Okay, does anyone have another thought, something else that may come to mind? Okay, maybe this one is not so obvious. Maybe I'll, if I don't see anything in chat, maybe I'll spoil it. Okay, there's no canonical or unique answer, but one thing you could do is you could, instead of specifying this constraint matrix A explicitly, you could have a box that for any x tells you, yes, the constraints are satisfied, or no, they are not satisfied. And I'll tell you in a moment why that is interesting, but I'll just first draw my picture. So given x, right, the output could again be a bit. It could say 1 if, well, the constraint is satisfied, and 0 otherwise, okay. So when would something like this be interesting? This could be interesting if there's really lots of constraints in your linear program, right? Say, I don't know, millions, probably not a lot for Shandor, but say, I don't know, like lots of millions of constraints, okay? So if you have lots of constraints in linear program, you don't want to write down this gigantic matrix, okay? But rather you want to implicitly evaluate this, okay? And then there's other algorithms that kind of only need such an oracle. For example, I mean, the one that's not practical, but which I know well is the ellipsoid algorithm, that can then, at least in theory, solve these problems efficiently. Chandra, go ahead.
I will get back to this point. So you can set a pointer to me, and I'll pick this up. You can pass that ball to me with this separation optimization and all that. So we're working our way towards more linear programming. Then we'll do integer programming, and that comes up.
Awesome.
Let me put one final point.
But sort of maybe the high level point I want to make though is you have some search space. Okay, maybe this one is not convex. Maybe I'll try again. Yeah. Maybe this one is up. Well, this one is also not convex. But if I don't want to draw a sphere, maybe take this one. This even makes sense. So there's two. There's various ways of specifying such a shape. One is sort of explicitly. That's basically what happens on the left. The other is just there's some shape, and you get to pick a point. Let's say I want to know, is this point in it? No. This one in it? Yes. This one in it? No. Okay, and that's a black box. Okay, you can interrogate this region by a black box. Okay.
One final keyword for future memory reference is traveling salesman problem and subtours. But we'll get to that. So just so that you remember this when it comes.
You shall remember. Very good. Okay. I'll just summarize what we saw in these examples in this discussion, and you may ask, of course, questions in chat or by just speaking up. So what I think we saw in this discussion, right, we saw that there's sort of, well, two natural, I mean, this is sort of artificial the way I set up, but there's two natural types of problems. One where the input is given explicitly, right, just, digits, formulas, vectors, arrays. The other is where the input is given by a black box, or we prefer the term oracle often, okay? So I'll just summarize this. So as we see, it's two natural, and I think both. I hope the examples made it clear that both of these are very natural ways of setting up the problems. They're different, but it's not like one is artificial and the other is, more privileged. It's just that maybe it's more familiar to us to think about something where the input is given explicitly. But actually, the right-hand side is very powerful because it sort of allows us to, build things that can work with arbitrary subroutines. So the first one, part A, there the input is given explicitly. And part B, the input is given in terms of a black box, so given by a black box or oracle. Okay. Explicit is clear, it's kind of all these examples, explicit arrays of numbers, explicit list, digits, vectors, circuits, formulas, all this stuff. Okay. Any questions about this? Okay, so this is sort of maybe an important distinction. Good. So now, we can maybe, so this is sort of addressing the first problem, how would an input be specified? And both of these models, they make sense for quantum algorithms, just like they make sense for classical algorithms. This one seems simpler, right? When the input is given explicitly, in the end, it all boils down to long strings of bits, right? We could just put these bits somewhere here, okay, at the beginning, and we start computing, okay? Or we could kind of feed these bits to the classical computer that controls the quantum one, right? And it could inform the circuit that's being run based on this input, okay? But it's a bit less clear how we model these black boxes, these oracles on quantum computers, and we'll come back to that in a moment, okay? Before doing that, though, I want to discuss the second question I wrote here. How do we quantify advantage or efficiency or complexity of an algorithm? So that's the second question. And that question is informed by the discussion we just had, right? Because if you're given explicitly, well, the only thing we're going to do is we're going to apply gates or elementary operations, that we sort of associate with sort of a cost of one, okay? that leads to what's known as time complexity in computer science. However, if we work in this black box, in this oracle scenario, there's another figure of merit that we could look at, namely the number of times you have to ask a question to the oracle, the number of times you have to call the subroutine, in other words. And that is known as query complexity. Well, it's very natural, of course, but oftentimes that's what dominates cost. I mean, not in the toy examples that you'll see in a moment, but in practice, right? If we minimize a complicated function, the cost, it's natural to count how often do we actually have to call this function. It may involve lots of things. But if you query a database, the database cost will be, the query time. Maybe it's even like in a different network or a different computer on the network that will dominate, not the little post-processing you do on your computer. Okay, so I'll write this down while we meditate about it. So we quantify the efficiency, or we often say complexity. Sorry, I'm not sure why my handwriting is so terrible when I write on standing desk mode, of an algorithmic solution or of an algorithm. That's all right. Yeah. Accordingly, maybe I'll actually write algorithmic solution because this is all in reference to a certain computation problem. We now discussed what these computation problems would look like. Accordingly. Okay. So, and sort of in the first case A, some of the only reasonable thing, or the only thing that maybe comes to mind, is we count the number of gates if we are in the circuit mindset, or the number of elementary operations. If we are sort of more in a code mindset, required to solve the problem. Okay, and usually there's some parameter in the problem, for example, the size of the list, the number of digits in our number, and then we're interested in how many gates do we need as a function of the size. Okay, to factor an n-bit number, how many gates, how many steps do we need? Okay, so this is what's known as time complexity. But if we are in this oracle scenario, there's a second option where we discard everything except the calls, the queries to the oracle. Okay, I mean, of course, we could look at both. That would be complicated again. But the simplest thing, which is still interesting that we could do, is we count a number of so-called queries, which is just fancy terminology for calls, to this black box or oracle. Again, require, the number of calls required to solve the problem. Okay, and this is what we call query complexity. Okay, when we worry about hard things like P versus NP, then sadly we're in this left domain, but the right domain is already interesting. It's much simpler, it turns out, to analyze, and I think logically this should be green and not blue. Okay. This one is much simpler to analyze because we ignore the details, we ignore all these little gates that we applied. We are just counting how often do we invoke this black box, how often do we query this oracle. And if you think about it, for example, when we, well, it's not so clear from this continuous example that Chandra and I discussed, but say this numbers game, right, where I sort of had a number in mind that you had to guess. It's really about information, right? You make one call to the oracle, you learn something about the function. And so, each call gives you one bit. And so it's easy to imagine that there's some more like, information theoretic argument going on there. While if you worry about time complexity, I mean, you're sort of faced with the full difficulty of the problem of, understanding all algorithms and so on. You can so that, I mean, it's difficult to appreciate if you haven't done this exercise yourself, but maybe we'll see in a moment why, at least for some problems, it's easy to argue in this query complexity world, because it abstracts away a lot of the baggage, right? It abstracts away all the boxes except for the ones we call this oracle. Okay. Yep.
Can I say two things?
Yep.
One thing is it's 4:30, but just to give you a chance
I will
to
come
ponder
back to
this for a
that
second.
After your second comment.
So when you think of a game, it maybe is a good idea to think of this separately. When you think of a game where you spend time thinking about what you're doing, but then you're making specific moves, and you may do a smart move in some way, but you may have to think about it. So there's a different way of measuring these things.
That's a
Maybe as
fantastic
metaphor.
analogy, right? I mean, just to make it clear, and in the analogy, if I understand you right, the thinking part is kind of all the little gates we do before we decide how to query the black box next, right? And the move is kind of querying the black box, yeah.
Everybody has sat down
yeah,
with a strategy game, with a chess or a board game, and you think and you think and you think, and then you do something, and that's the query that you're doing. And
yep. Well, that's an excellent analogy. It's a bit like, you know, maybe you're faced with some complicated chess situation, and you know, scenario A, there we're like measuring how many hours does it take you to, you know, I don't know, beat your opponent. And option B, you're asking how many moves do you need to make, you know, say in the best case to beat your opponent. And you can think for as long as you want, basically, no time limit. Yeah.
And sometimes it is much faster. I mean, when you do a Sudoku, for instance, you could think of just trying out the numbers, and sometimes that's much faster than if you just think all the logic or so on. Yeah. Anyway.
Good stuff. Yeah. So indeed, so it's past. So what we managed to do so far, just to zoom out a little bit. So before I promised you that perhaps today, but certainly not today, we will discuss simple problems where quantum algorithm advantage. Now we can make this a bit more precise. So one thing we can do is, for example, we can say next time, or in a future time, we will discuss simple oracle problems. So ones that involve these black boxes. Where quantum algorithms give an advantage in query complexity. Okay. Query complexity advantage. And I mean, I don't want to just let you leave without having one concrete example in mind. So I'll give you one, and it looks incredibly simple. And nevertheless, there will be difference quantumly and classically. Okay. And I call it Deutsch's problem because it's the problem that corresponds to the algorithm by David Deutsch. That's a special case of Deutsch-Joseph. Yeah, so I want to still present this, if that's okay. That will take a couple minutes, and I think then maybe I think in a future session we'll talk about what does actually a quantum oracle look like, why is it an okay notion, and how does the quantum solution work. And you know, sort of how does it fit in to the picture? What are sort of more realistic problems? Okay, so this will be a toy problem, so I warn you. But nevertheless, it's kind of striking that, you know, by changing the games and by doing quantum, we can do better. Okay, so at least in principle. So we'll call this Deutsch's problem. And the problem is the following. So the input is a function, a black box function. Okay, so we have a function, and it's a function from a single bit to a single bit. There's not so many such functions. There's 4 functions in total, right? There's the function that's always sends any input to 0. There's the function that's constant 1. Then there's the function that sends x to x, and there's the one that says x to its inverse. Okay, so these are all the options that exist. So there's 4 different functions from a single bit to a single bit. 2 of them are constant functions. The other half, you know, well, they're not constant. They're either doing nothing or they're flipping the bit. Okay, keeping that in mind. The goal of the problem is the game that you want to play is the following. You're given, or maybe David Deutsch gives you such a function, you know, black box access, oracle access to such a function, and you have to decide if it's a constant function or not. Okay, so the goal is decide if such a function on a single bit is constant or not. Okay. So the input, just to be very precise, it's oracle access to a function on a single bit, which is exactly, you know, you can interpret in the way we discussed it before. And if you want to be super picky about the output, right, maybe we want that the output is, let's say, 0 if the function is a constant function, and 1 if f is not constant, so otherwise. Okay. So last thing we want to discuss today is how well can you do with an ordinary classical algorithm? Okay, and I want to have, again, right, we're in this setting of Oracle problems. So basically we play a game. I have a function in mind. You get to ask me questions. There's only two questions, f of 0 and f of 1, right? That's the only thing you can ask me. You can say, what's the function value at 0? What's the function value at 1? And I want to understand, I would like you to think about what's the query complexity of this problem. That is, how many such questions do you need to ask me in any case, in this case, to figure out if the function is constant or not, okay? Does anyone have a thought about this, a reaction, or maybe a clarification question about how the game works? So you can imagine I am this box, you get to ask me questions, you tell me an x, I tell you f of x, and your goal is to figure out whether I represent a constant function or whether I represent one of these other two functions. Timo.
To get a result with certainty too.
That's right. So why, I guess 2, because if you ask two questions, you know the function anyways, right? The whole function.
Yes, but if I ask you, if I give you the 0 and you tell me 0, then it could be that like the identity, but it could also be a constant. Whereas I could be lucky and I tell you 0 and you tell me 1, then I know that no, that could also be the constant function. So I have to ask you 2 times. Yeah, I could not.
That's right. You're completely right. From an information point of view, knowing one function value is completely independent from the other. So knowing f of 0 is completely independent from f of 1, but the property of being constant depends on both, right? In a non-trivial way. I mean, basically by checking that f of 0 equals f of 1. So just knowing f of 0 does not tell you anything about constantness. Just knowing f of 1 does not tell you anything about constantness. So you need at least 2, and 2 is enough because the function is fully specified by 2. So that's exactly right. So clearly, and now we can boldly say clearly because we had this nice discussion. Any classical algorithm, and randomness does not help, any classical algorithm will need 2 queries. Okay. We have to ask this black box 2 questions. Okay. And what we'll find next time is, next time we'll discuss, okay, well, the natural question is, can a quantum algorithm do better? In order to answer this question, we have to ask what even is a quantum oracle, right? Right now, I just know x goes to f of x, but what happens if I put in ket 0 plus ket 1? What should that do? Should it be ket f of 0 plus ket f of 1? Does that make sense? So we have to have a little discussion about this, but then the upshot will be that there's a quantum algorithm, Deutsch's algorithm, which can solve the same problem using a single query. So we use this black box, this oracle, only once, okay? Of course, we use it in a more general way, and then we have to discuss, am I cheating? Am I not cheating? I'll convince you that we are not cheating. We can discuss about the importance of this particular problem. But sort of the answer, basically, roughly speaking, will be the following. Whenever you have a black box, so whenever you open the black box, okay, inside is actually a little circuit. There's a completely mechanical procedure that replaces the circuit by a quantum circuit of the same complexity up to a negligible overhead. That implements the seemingly more powerful oracle. So I'm saying this for Shanda because he was skeptical about that we are not cheating. And so that's the reason. Okay, so that's a very good explanation why this is fair. I mean, the other question is, of course, that, you know, in this particular problem, the cost will be anyways dominated by this box, and, you know, not the number 1 or 2 will maybe not so be important. So we want to, of course, also discuss more general problems where there's actually something that become large, maybe where there's an exponential separation between classical and quantum, and so on and so forth. Okay. And of course, to really prove something very convincing here, that's, you know, as hard as proving, say, P versus NP. So, you know, we're working on it. Okay. So, but sort of in this oracle setting, we can make very precise statements, very precise separations, and I think also very convincing ones. And yeah, so maybe that's a good way of stopping here, and maybe just asking you for questions or feedback or thoughts.
Well, first of all, let's thank Michael. That was fantastic. I really appreciate it.
Thanks.